So things seem to have naturally quieted down, although I was going to keep writing for a few lines as review while you guys chatted, but I guess now I'm forced to start. All right. Do we have any announcements, Larry? I can't remember if we have any things to say. The first homework should be on the website. It's due a week from this Friday. So that's January 23rd, if I'm not mistaken. Projects, talk with people to find a project partner. We recommend that you work in groups of 2. You'll find out some information about the first milestone for that project soon. Did I miss anything?
The link to the video is not up yet, but will be as soon as we get it.
Yeah, that's right. So the videos are being recorded, and then we're going to post the videos off the course website, but the first one hasn't come yet. Piazza, actually, that's another thing. Piazza, right? I think most of you guys should be signed up for Piazza automatically. We enrolled all the people who were registered in the course on Piazza, but if you didn't get enrolled for whatever reason, you can just go to the course website and sign up. Click on the link for Piazza and then sign up there. We're totally fine if you want to sign up for that the Piazza group, even if you're not actually officially enrolled in the class, that's fine. I think it's really useful for class discussions and questions. Okay, I guess that's it for announcements. So today's going to be review. We're going to move kind of a little quicker than yesterday in the sense that we're going to try to cover a little more stuff in terms of the bias variance trade-off, and then we're going to get to some stuff on model complexity in degrees of freedom, and then some stuff on cross-validation, and then some stuff on what we call linear smoothers. Some of this might not be review. So we might get to a point where you guys haven't seen one of these topics, but that's fine. And the course website has the document that I'm going to go off of. It's called Modeling Basics. It should be review part 2. So here's where we ended up last time. Actually, one more line after this that I was going to write. So I'll just do that right now. So if suppose I'm given n IID pairs xy, that means that xi, yi's are IID pairs. And I have another point xy. And these are my training samples, and this is a test point. All independent, all the same distribution. And I'm going to fit f hat on the training data. That's some function that tries to predict y from x. And remember that we can always write y as some underlying function f of x plus epsilon, where epsilon has mean 0. We're always able to do that because we just take this f of x to be the conditional expectation of y given x. And that, this decomposition always holds if we take f to be the conditional expectation. And then this is what we call the prediction error, or the expected prediction error. And what I've done is I've actually wanted to focus that we're going to condition on a particular test input x. So last time I wrote it as an integral, and I went a little bit fast, so this may have been lost in the details, but I'll be clear now. We're interested in predicting y from x, but we're interested for the moment not just looking at a particular point, little x. So this is the expected test error, or expected prediction error, at x. And it decomposes into a bunch of informative parts. First of all, we can always write it as sigma squared plus what we call the mean squared error, or the risk, at x. And the variance of epsilon we're just going to denote by sigma squared. So that came from. So this is called the irreducible error, or the Bayes error. We can never get rid of this part. It's always true that the prediction error and expected prediction error is always sigma squared plus the mean squared error. The mean squared error further decomposes into 2 parts, called the bias and the variance. The variance, there's only one way to interpret that, right? That's the expected value of this random variable f hat of x. It's random because it's fit on the training data, x1 through xn, right? minus its expectation squared. In fact, I'm just not going to get rid of so many parentheses. That should be clear. The bias is equal to the difference between the expectation of our estimator and the true regression function f of x. So the squared bias is just this thing squared. All right, so that's the bias variance decomposition. How do we prove it? We didn't prove it last time, and I'm not going to prove it now. I'll just say in words, and if you are unclear about what I'm saying, then try on a piece of paper after class. Add and subtract f of x from this expression and expand the square, and we get this from y minus f of x squared, and we get this from f hat of x minus f of x squared, and the cross term is 0, you'll see. So now we have this. How do we go from the mean squared error to the bias variance decomposition? Well, we're going to add and subtract the expectation of f hat of x. So if we add the expectation of f hat of x and look at the term that's f hat of x minus its expectation squared, it's exactly this. I'm sorry, this is the term that looks like the expectation of f hat of x minus f of x. And the other term, which is f hat of x minus its expectation, is exactly this. It's the variance. And how about the cross term? The cross term is again 0. Okay, and here's where it's important that I conditioned on x, actually. That's why I did that. Because you can see that by conditioning on x, this is only random due to the training set, which was useful for this decomposition. All right, so that should be something that you've seen before, pretty familiar with. How do we get the unconditional test error? Well, we just integrate over x. So that's what I had written down last time. Right, the expected value of y minus f hat of x squared is just sigma squared. If I integrate over the distribution of x, it doesn't matter. Doesn't change it. Plus the integral of the squared bias at the point x times the to the density right of x plus the squared bias plus the variance of f hat of x density of x. So that's what it looks like unconditionally. And that's what we'd seen last time. So this says that the expected test error is the average bias plus the average variance plus sigma squared. All right. So let's do an example of the bias variance trade-off. Can you guys see if I write over here? Everyone can see this? Try to write big. So let's think about k nearest neighbors regression. So let's think about f hat to be the k nearest neighbors regression estimator. Okay, and what is that? How is that defined? I hope you guys are all familiar with this from another class, but we'll certainly cover this in the nonparametric regression section in more detail. So at a point x, right, if you want to make a prediction on x, what you do is you take 1 over k times the sum of all points I that are in the neighborhood of this point x of size k, and you average their y values. So in other words, it's saying, look at the nk of x is the, these are the k closest points to x. Whatever the point is at which I want to make the prediction, find those guys, add up their y points, and divide by k. So it's just a local average. That's all it is. That's the k nearest neighbors regression fit. Let's try to derive the bias variance trade-off for this guy. And we're going to see how where k comes into it, right? So intuitively, what happens if I make k really large? What should happen to the bias, for example? Bigger or smaller? If k gets large, the bias gets smaller. What happens if k is n? What am I doing then? How am I estimating at a point x? just giving y bar. So what do you think the bias of y bar is going to be compared to the bias of like the two nearest neighbor regression fit? Large, right. It's not nearly as flexible. It's a very restricted class. We're just taking an average of all the y points. Okay, so the bias gets big as k gets big. What about the variance? Right. So as k gets big, we expect the variance to get smaller because when k is n-word fit in the mean, that's pretty stable compared to like a two nearest neighbor regression fit. Okay, so let's look at the decomposition now. We'll just try to write it down. And here's where you can see that depending on the situation, it helps to treat x as fixed or random. So here we treated x as random. That's kind of the most generic, or on a very generic model. For the k and n fit, it's going to help to treat x as fixed. So it's just one example where it'd be harder if we thought of x as random. Okay, so let's think about fixing x1 through xn. And that means that when we talk about like expected prediction error, we're talking about the expectation over y, thinking of x as fixed. What's the at a new point y, right, what is the expected prediction error, expected test error? It's sigma squared plus the bias squared plus the variance. So let's look at the bias first. The bias is the expected value of f hat of x minus f of x squared. That's f hat. So what's its expectation if I consider x as fixed? The only thing that's random here is the y's, right? So the expectation moves through. X is fixed, right? So this index set is fixed. What's the expectation of yi? It should be f of xi, right? Because that's the expectation. F1 is mean 0, so the expectation of y is f of x. So the bias just looks like 1 over k times the sum of f of xi minus f of x I in the k nearest neighbors of x. Okay, so we'll get back to that in a second. It's a squared bias. What's the variance? So again, all that's random here are the y's. The x's are fixed. So what's the variance of this expression? What's the variance of, first of all, are these y's independent? They're independent, right, because I'm assuming the x points are fixed. And I guess maybe I should have been even more explicit. When we assume that the x points are fixed, we kind of have to assume that the points are independent unless we assume some specific variance that depends on x. So here we're assuming that the y points all are drawn from this model with fixed x, and the variants are all the same. And so I get that the variance of this guy is just 1 over k times sigma squared, right? Because each of those has variance sigma squared. So that should be the variance of f hat. All right, so let's see, how does k figure in? When k gets big, this gets small. So we were right. When k gets big, this is likely to get big, right? Because this is probably going to be pretty close to this if f is smooth. If f is smooth, and I take an average of nearby points, then it's going to be close to f at x. If I take an average of all the points, so I take an average of the nearest n over 2 points, where n is very big, then that's not necessarily going to be that close to f of x. So now we can actually already see how we might even prove consistency for the k and n fit. We're not there yet because we haven't made any conditions on f and stuff like that, but we'll get there pretty soon. I have to make the bias and the variance both go to 0, right? I have to choose case where the bias and the variance both go to 0 in order to get a consistent estimator, if I want to make sure that the mean squared error goes to 0. So how do I make sure that this goes to 0? I have to make sure that k goes to infinity, right, as n grows. Okay, so that's not too hard. I have to take an average of bigger neighborhoods as I observe more data points. It's pretty reasonable. This one, it's not so clear what you'd have to do in order to make the bias go to 0. But if we had some smoothness conditions on f, like if we said that f was, for example, Lipschitz, which means that its derivative is bounded by some constant, then we could start to see how we could make sure that we could take a neighborhood that was small enough that the average of points in the neighborhood converged to f of x. So it turns out that actually root n will do it. If we take k to be root n, we'll get a consistent estimator with some pretty weak conditions on f. So there you go. That's how we use the bias variance trade-off, for example, to prove consistency of k and n. Any questions about that? Because that's going to be most of the end of the bias variance trade-off for us. I mean, you'll see it on the homework again, so you'll get to enjoy it one more time. But for the lecture's sake, we'll be done with it. OK. So here's now a part that we're going to talk about how to estimate the expected test error or the expected prediction error. So we've seen why it's important, right? It's important for purposes of model selection, like in the k and n problem, informing us about how we might choose k. How might we estimate it in practice? Because we can't ever exactly compute this expected test error, right? It depends on the unknown distribution of x and y jointly. So, all right, if we had pairs x1, y1 through xn, yn, that was our training data we used to fit f hat. Somebody gave us magically m IID pairs x prime, y prime from the same distribution as these guys. So right, we use these to fit f hat. Then if I just took the average of yi prime minus f hat of xi prime squared, and that's going to be an unbiased estimate for the expected test error, right? So in expectation, this is just kind of like a vacuous statement, right? The expectation of this estimate of the test error is, of course, expectation of y minus f of x squared, right? Xy is just one such test sample, and here are m of them. So this is a good estimate for it. Why are we taking a bunch of them? Well, because not only is it unbiased, but the more I take, the more test samples I observe, the lower the variance of this estimate is. So, okay, so we know if we had test data, we would just compute the observed test error, which is this guy, and we'd claim, oh, it's pretty close to its expectation, which is the expected test error. Sounds good, but we rarely have test data in practice, right? We're usually short on data. Or at least we want to use all of our data for training purposes. We don't really ever put aside a test data set unless we're in kind of a very fortuitous situation. So this is the observed test error. What about the observed training error? Is that a good estimate of the expected test error? Shouldn't be, right? This is like, again, basic stat ML. This is going to be way too optimistic in terms of trying to get at the expected test error. Why? It's because f hat was chosen to make this quantity look small, or quantity like this look small, right? We maybe didn't minimize least squares loss explicitly to get the function f hat, but we probably did something in the training set that tried to make this look small. So of course, when we evaluate it then back on the training set to look at the error, it's going to look way too optimistic as an estimate of what happens for a future prediction, a future point xy. That wasn't one of the ones we used to train f. So that's, kind of a conundrum that we always face. But here's something very specific that we can say about how these two quantities differ if we're willing to assume, again, another example where we assume that the x points are fixed. And we can actually compute the training error of the optimism of the training error, explicitly, and we can see how it can be even computed in some cases. So that can actually be a very useful thing. And it's going to lead into what we call degrees of freedom. So let's do that. Just going to go right here. So I'm going to assume a more specific model than I did for this, because I want to be able to say more, and it helps if I assume the x's are fixed. So I'm going to assume that the yi points are some function f of xi plus epsilon I, and the yi prime points are some function of xi plus epsilon prime, where I suppose I have m test points and n training points, and all these epsilons, right? Epsilon I, epsilon prime are IID with mean 0 and variance sigma squared. So what are we assuming here that's more than usual? Well, we're treating x as fixed. It's one thing. The hugely offensive assumption we mentioned last time is that we're treating the epsilon i's as IID. So in particular, they don't depend on x, right? And that was something that we said last time is definitely an assumption. It's not always true. And it assumes away the fact that we could have left out some variables that were important, right? The variance you can see of epsilon is just sigma squared. So we're not saying it depends on x at all. And lastly, we're assuming that we're in a pretty fortuitous situation where the test points are being observed at the same input locations. So y prime is equal to f of xi, and yi is equal to f of xi. So these guys are like duplicates of each other, independent duplicates. OK, so certainly not the most generic situation, but it's still a fairly broad one. And now we're going to relate the expected test error to the expected training error. And I'm going to write everything as a vector. So I'm going to write y as a vector that contains these components. Since we're assuming they have the same input locations, that we have the same number of test points, I'm going to write y prime as a vector with these components. And when I write f, I just mean the vector with these components. So the first component is f of x1. The last component is f of xn. So what's the expected test error? It's exactly this guy. So I'm just using some shorthand notation saying that we fit f some function here, and we're going to shorthand it as a vector whose components just give us the fitted values over the points x1 through xn. So that's the expected test error. And it turns out we can actually decompose this in a way that's kind of analogous to the bias variance trade-off, but it's not the same, to get an idea of how different the expected training error is from the expected test error, and that's called the optimism. So let's just add and subtract. Start off by adding and subtracting f. So we'll use the same notation for f as we did for f hat. It's just the function evaluated at these endpoints. Let's add and subtract f in here. Okay, so this is equal to y prime minus f plus f minus f hat squared. And now let's expand the square. So we're going to get a term that looks like 1 over n times the expectation of y prime minus f squared plus 1 over n times the expectation of, you can write it as f hat minus f squared plus the cross term. Okay. By the way, do people know what this notation means? This is just the L2 norm of a vector, right? So it's the sum of the squared components. This is exactly what I had before. Just treating everything as vectors. So what does the cross term look like here? It looks like 2 over n times the expectation of y prime minus f transpose f hat, or f minus f hat. Okay, I claim that cross term is 0. Why is that cross term 0? I heard some good stuff, but it was all at once. So first of all, this is what's random here, y prime. F's not random. What's random here? It's f hat. F hat's a function of only y, right? It's fit on the data set y, y1 through yn. So these two parts are independent. So that means that I can take the expectation of each part. I can move it in, right? What's the expectation of this part? Well, we don't really know. What's the expectation of this part? It's 0, right? So this whole thing is 0. OK, that's helpful. How about this guy? What is this here? Expected value of y prime minus f squared. Summed up over the n components. So this is the sum of the expected value of y prime minus f of xi squared, right? But f of xi is the mean of yi prime. So it's the sum of n n random variables around their mean squared. So it's just going to be sigma squared, right? Because I have the 1 over n in front. All right. How about this term now? So this term 0, that term sigma squared. This term is what we're going to decompose a little bit further. And we're going to do so by adding and subtracting, again, as we did before. This time we're going to add and subtract y, actually. So you'll see why we want to add and subtract y. It's because I want to relate this to the training error somehow. So I want to get a term that looks like the expected value of f hat minus y. Plus the 1 over n times the expected value of y minus f squared plus 2 over n times the expectation of f hat minus y transpose y minus f. OK, so what's that? Is that 0? No, it's like the only time in these decompositions that I actually make a cross term and it's not 0. So I was just seeing if anybody would fall for it, but I'll just leave that there. What's this, though? Expected value of y minus f squared over n. That's just another sigma squared, right? It's the same thing as before. So I'll just put a 2 sigma squared there, and I'll forget that term. So I have 2 sigma squareds now. What's that? That's the training error, right? That's the expected training error. OK, so we're looking pretty good. We have that the expected test error is 2 sigma squared plus the expected training error plus something. OK, so this thing we need to understand a little better. So let's split it up into 2 parts. Go up here. So I'm going to think about it as, right, as first the expected value of f hat transpose y minus f minus the expected value of y transpose y minus f. Split it up into those 2 parts. Minus expected value of y transpose y minus f. What's that? So this is a trick we can always do. If we ever have like the expected value of something times another thing that has mean 0, we can always change the constant term here, right? I can always write this as y minus something transpose y minus f. Because if I stick in a constant here, if I write like y minus c transpose y minus f, and I expand that out, then the first term looks like this, y transpose y minus f. The second term looks like c transpose y minus f. But c is a constant, and y has mean f, so that didn't do anything. So I can always actually add in whatever term I want here, as long as it's a constant. So let me just add in f. OK, that means that that's actually equal to minus 2 sigma squared, this part. That's equal to minus 2 sigma squared. It's minus 2 over n times the norm of the expected value of the norm of y minus f squared. So that canceled with the first part. All right, so now we are looking pretty good because we say that the expected test error is exactly equal to the expected training error plus this part. That is what we call the optimism. It's the difference. It's how optimistic the training error looks compared to the test error. And we can rewrite it another way that makes it more clear. Again, I can use the same trick in that I can actually subtract off anything I want from f hat, because this has mean 0, as long as I'm subtracting off a constant. So I'm going to go ahead and subtract off the mean of f hat, which makes this the sum of the covariances of f hat with y. So let me write that up here. All these steps, by the way, are pretty much laid out in the notes, so if you didn't write them down, don't worry. Just want to write down the punchline. Times 2 over n. So this is the amount by which the training error is too optimistic. We can think about it in a bunch of different ways. The way that I think is probably more easier to remember is to write this as 2 over n times the sum from I equals 1 to n of the covariance of f hat I, f hat of xi, with yi. If I just write this out as a sum of n things, each of those things is this. It's exactly the expected value of the ith component of f minus mean times the ith component of y minus its mean. So this is what we call the optimism. And we can see that it describes how influenced the ith fitted value is by the ith data point. So if these two have very high correlation, then we can see the optimism is very high, right? If the ith fitted value depended a lot on the ith observation, then you can guess the model is probably more complex, which means that the training error is going to be even more optimistic. The test error is given by training error plus something bigger. So that's the optimism. So that, I don't know, that may or may not have been new. It's something we teach usually in statistics, but maybe not in machine learning. And this leads right into nicely a natural concept called degrees of freedom. And degrees of freedom is defined pretty much right off of this expression. So I'm just going to move things around so I have a little more room to write. Right, this was the sum of the covariances of f hat of xi with yi. We write this as 2 sigma squared over n times the degrees of freedom of f hat. So in other words, we're just defining the degrees of freedom of f hat to be this sum of the covariances over sigma squared. You may have heard this word degrees of freedom in other contexts, like we say, a random variable has a chi-square random variable with so many degrees of freedom. That's a little bit different usage than this one, although they are kind of related. But when we talk about an estimator having a particular degrees of freedom, this is what we mean. That its degrees of freedom is equal to the sum of the covariances of its fitted values with the observations divided by sigma squared. And we can think about it like the effective number of parameters that are used by that estimator. That's a pretty common interpretation of degrees of freedom. So let's go through some examples of degrees of freedom so you can understand why we're talking about effective number of parameters. So remember, right, df of f hat is 1 over sigma squared times the sum of the covariances of f hat of xi with yi. So I have some simple examples here. Let's suppose that I took f hat to be y. What's the degrees of freedom of this estimator then? The estimator is, you give me points, pairs xi, yi. I tell you my prediction at point xi is yi. It's pretty naive. What's its degrees of freedom? N, right. So and first of all, intuitively that makes sense, right? That's the number of the kind of number of effective parameters it's using, because I observe n things, I'm predicting n things, and I'm just predicting what I observe. How do we see that formally? Well, I'm taking the covariance of, right, its degrees of freedom is 1 over sigma squared times the sum of the covariances of yi with yi. Each of these is just the variance of yi, which is sigma squared. There's n of them, so I just get n. N sigma squared over sigma squared. Okay, that makes sense. How about if f hat got what I had next is the mean, is y bar, I guess. What's the expected number of parameters? So this is the guy that you give it n observations, and you're supposed to make n predictions, and it just returns y bar for everything. What's its degrees of freedom? So I'm taking the sum of the covariances of yi with y bar. What's the covariance of yi with the mean of y1 through yn? No, it's not 0. Because there's a yi in there. It's what? Sigma squared over n, right. Because the mean is 1 over n times the sum of all the points. Yi is uncorrelated with all the yj's for j not equal to I, but it has, its variance is sigma squared, so the covariance of 1 over n yi with yi is sigma squared over n. So that's sigma squared over n. There's a sigma squared here. I have n of them, so it ends up being 1. So that makes sense too, right? We're estimating one parameter, just the mean. So it all checks out. And what if f hat was at a point xi was given by taking the average of all points in the neighborhood of x of size k of yi. This is exactly actually the k and n fit. Right? I'm treating x as fixed. Remember, that was what we did at the start of all this. So only y is random. What's the degrees of freedom? First of all, don't even think formally. What should it be intuitively? How many parameters are we fitting when we do k and n? Roughly fitting k, right? We think that should be the case because every time we're making an estimate, we're just taking an average of k things. So we're considering k things to form our estimate. Is that true formally? Yeah, it's true because you can just check right here. What's the covariance of this with yi? Well, it's I should write this as j so it doesn't confuse you. And then this is the neighborhood of xi. Right? I'm taking the average of the points in the neighborhood of xi. What's the covariance of this with yi? Ends up just being the covariance of this with yi? Sigma squared over k, right? So actually this is wrong, obviously. So I'm glad that no one caught me. Right? It's sigma squared over k. So the degrees of freedom should be n over k. Okay, so why does that make more sense than k? Well, think about the extremes, first of all. What is n nearest neighbors regression? It's just the mean. Right? So that was this guy and has degrees of freedom 1. What was 1 nearest neighbors regression? It was the guy that turns back y1 through yn and has degrees of freedom n. Okay, so that makes sense here. And now it does make a lot more sense, right, if you thought about it, that with more nearest neighbors, we have fewer degrees of freedom. Because like effectively at large, the estimates are less flexible. So that's the answer. The note says k. I don't know why I wrote that down. That was clearly a typo. So here's a couple places where we see it check out, match our intuition. It's actually really useful here, right? Because look, we actually can look at the training error, and we actually knew what this was exactly. for a bunch of different estimators. They were pretty simple, but we knew what it was exactly. So for k and n, for example, I wrote down that the excess, the optimism between training error and test error should just be that. So the training error looks too small by a factor of 2 sigma squared times k. So if you fit a k and n regression fit and you look at the training error, you should expect the test error to be larger by this amount. But that optimism is bigger the bigger k is. Right? Because here we had 2 sigma squared over n times the degrees of freedom. The degrees of freedom we said was n over k. It should be 1 over k. Seems like I really want to put the k in the numerator over and over again. Okay, so optimism, or degrees of freedom, provides us a way of explicitly looking at the difference between training and test errors. And all right, truthfully, we can't always do this. So we can't always compute degrees of freedom. So it may seem like I'm coming up with pretty simple examples to show you. But there's one thing that's very, very useful about this formula, and that's forming an estimate of the test error based on training error and degrees of freedom. So we'll get to that next. But there was a question here, I think.
Yeah, can optimism be used to estimate sigma squared?
It's a good question. So here I'm assuming sigma squared is known, right? So if you're going to use this in practice and you don't know sigma squared, you have to estimate it. Optimism itself, I don't think that's... I'm not sure how that would lend itself to an estimate of sigma squared unless you had test data available, right? If you had test data available, then you could actually empirically evaluate this difference and then use that to estimate sigma squared. But I'm not sure, short of that, how you do it. We'll talk about cross-validation after we talk about this stuff, and which you see doesn't really make any of these assumptions, doesn't depend on sigma squared, so in many ways is more robust. Okay, so let me raise this issue of estimation, test error estimation. I want to actually get an idea of the estimate of the test error when I don't know degrees of freedom. And then after that, we'll take a quick break. So let's just look right here, and let's form remember this was 2 over n sigma squared times df of f hat. Let's consider forming the following estimate. We'll call it t hat, because it's going to be an estimate of the test error. It's going to be the observed training error. Remember, even this I don't actually know typically in practice, right? Because I don't actually know the distribution of the training data. So I'll just take the observed training error plus 2 over n times sigma squared times df hat of f hat. Okay, so it may look like there's a lot of hats going on, but I hope this is not too confusing. This really just means an estimate of the degrees of freedom of f hat. So one that has, we're going to actually assume that we have an estimate that has the following property. Suppose that we had an estimate of degrees of freedom that was unbiased. So on average, it told us the right degrees of freedom, where this average is taken over the training data. Then what do I know about t hat? Well, take the expectation of t hat. What do you get? You just get this, right? Expectation goes through. Expected value of df hat is df. By assumption, expected value of the training error is the expected training error by definition. So we get that the expectation of t hat is equal to the expected test error. So I don't have a handle on the test error per se, but at least I can estimate it via this formula right here. This was actually a really, really important fact that I guess was discovered at some point in statistical prediction theory and was leveraged in many, many different ways. So from this, you'll see a bunch of different things that all have the same name. This, for example, is what led to the CP criterion which is very closely related to AIC. So in regression, we kind of see that we can exactly, if we do regression of y on p predictor variables, then degrees of freedom is p. So in fact, it's not an unbiased estimate. We know the degrees of freedom exactly. And the CP criterion is to take the observed training error plus 2 over n sigma squared times p, and to call that an estimate of the test error. And we know that actually it's unbiased from this fact. So if we have the degrees of freedom exactly, that's even better. If we don't, then we can take an estimate of it, and then our estimate of the test error is still unbiased from this fact. So because we actually can look at estimates of degrees of freedom, this opens up our class of things that whose test error we can estimate to be a much, much more broad class than the ones whose degrees of freedom we know exactly. So we'll return to this later in the course when we talk, if we get to Stein's lemma. I guess depending by the end of the course depending on people's interest, we may choose to cover some topics. One of the topics we can cover is Stein's lemma, which gives us a prescription for how to compute unbiased estimates for basically functions that are smooth. So it's a very, very broad prescription. And in many cases, these estimates are very, very simple, easily computable, and they lead directly to estimates of the test error. So it's a really, really useful fact. We might use this for model selection, right? For example, if we had, if f hat was indexed by a parameter called theta, and we knew what the degrees of freedom of f hat was as a function of theta, then we might try evaluating this test error estimate at each tuning parameter value theta after we fit on the training data and see which one gave us the lowest estimate of the test error. And then we choose the tuning parameter theta accordingly. So it gives us a way to do model selection, for example. Okay, I think we'll we'll come back to degrees of freedom even sooner than Stein's lemma when we talk about linear smoothers in nonparametric regression. Any questions about that? All right, let's take a quick break and then we'll come back and do cross-validation. All right, so just to be, I wanted to make that last point perfectly clear about model selection. So suppose we were able to compute an unbiased estimate of the degrees of freedom of some estimator at every tuning parameter value theta. So for example, theta could be indexing k in k nearest neighbors regression. And then this would be n over k. So I got it right, finally. This would be 2 sigma squared n over k, right? And this would be the observed training error of the k nearest neighbors regression fit. I could look at that over all possible values of theta, or k here. And I could choose the tuning parameter to make that as small as possible. That's a perfectly legitimate way to do model selection because this is an estimate of the test error. So here's a kind of circular point, but it starts becoming important. Suppose I chose theta hat accordingly. Theta hat was the minimizer of all of this stuff. What do you think? Let's call this t hat of theta. That was our estimate for the test error at theta, right? I chose theta hat to make this as small as possible. What does t hat of theta hat look like? Is that a good estimate for the test error at theta hat? Meaning, I have this procedure now where I fit some prediction function on data. The procedure is as follows. Try it for every tuning parameter value. Pick the one that makes this criterion the smallest, which I can evaluate. Call that theta hat. Then look at my prediction function at theta hat. That's the one I'm going to carry forward to make future predictions. Is this a good estimate for what the error looks like for its future predictions? T hat of theta hat? It's not, right? It's again too optimistic. So it's optimism kind of biting us once again. So we use optimism here now for model selection purposes. It was totally fine. Don't fool yourself into thinking this is actually a good estimate of its test error. It's optimism once again. So now here's where things get a little interesting. You can actually sometimes compute the degrees of freedom of this. So you can correct it once again. But we probably won't get into that. But again, at the end of the semester, we'll do some advanced topics if that's interesting. All right, here's your second SML joke. I was going to say it right when the break started, but I wanted to clarify that. I hope I don't get fired for this, by the way. So an experimentalist and his wife have a baby, and they have two babies, they have twins. And the experimentalist and his wife and the experimentalist's best friend, who's a statistician, of course, they go to church together. And after church, they go up to the priest, and the priest says, "Oh, these are beautiful kids," and turns to the experimentalist and says, "Should I baptize them both?" And then the experimentalist says, No. Baptize one. Let's save the other as the control." And he turns to the statistician for support, like, is this a good idea? And the statistician then looks at the wife and says, "How do you feel?" She says, "I feel fine." "Why?" He says, "Well, I think we need a larger sample size." Okay. I got better response for that one then.
I think you augmented the jokes this last week.
Yeah, I did. I added some parts to it. Okay, cross-validation. So, cross-validation is a favorite of many. And to put it simply, it's because it doesn't assume much. So Larry told me that if I didn't make all the assumptions about this optimism stuff precise, he would jump up and wave his hands and complain because he thinks it's partially bogus. So that's why I made the assumptions very, very clear, that we're assuming fixed x, and we're assuming that epsilon's independent of x. Cross-validation doesn't assume that stuff, right? We don't actually have to make those types of assumptions. So in a sense, it's much more robust to situations where we don't really know the data generating distribution. And so it's a very general tool. I'm just going to very briefly cover CV because I'm sure you've seen in other courses, but I wanted to mention a few subtleties. So we have IID pairs, x and yn. That's all we assume. All we assume is that these are IID. And we're going to split up these pairs into what we call folds. And these folds are disjoint. And their union is 1 through n. And we usually make this division in a random manner. So we divide the data up randomly into capital K folds. And then we're going to use this following notation. F hat of minus k for some, I'm just going to use something else because my capital K's and my lowercase k's probably aren't that distinguishable. So we'll use f hat of minus j to denote the fit, or the function that was fit on all folds except fj. So we train on all folds train on the data in all the folds except for fj, so we leave out part of the data. And then we're going to evaluate this quantity we call CVJ, which is 1 over nj times the prediction error when we look at all points in the jth fold. Did I use any k's anywhere? No, I think that's fine. So this is just saying we train on all but the jth fold. We evaluate on the jth fold, the errors in the jth fold. So that's this is fine because we didn't use this for training. So with respect to f hat of minus j, this estimator, this looks like independent and equal and identically distributed data, right? It was trained on stuff that wasn't in fj. So that's the error that we report from the jth fold. Remember, the thing about cross-validation is that we don't do this just once. We don't just leave out one fold like the first fold or something. We do this for every fold in turn. So we leave out the first fold, train on the rest, evaluate in the first fold, etc. And then the cross-validation error, which we usually write as CV without any subscripts. is just the average of these guys. Okay, how to choose k? This is a common issue we all encounter. So let's think about the most common choices. The most common choices I would claim are k equals 5 or 10. So 5 or 10 full cross-validation, but I'll just write 5, versus k equals n. One that people like to do, which is leave one out cross-validation. So in that case, each fold is a single data point, and we're just leaving it out in turn. And so we're fitting on all but the jth data point and then testing on that data point. So these are not the only two choices, but they're the most common ones. So let's discuss what the differences between them. So I'm not going to call it bias for now. Let's look at the mean of the CV estimate, right? So the CV estimate is trying to estimate the expected test error. So what happens if we take f hat, train on all of these pairs, and then test it on some new independent data? What does the mean of the CV estimate look like? Well, what does it look like when k is like, say, 2? So in that case, we're doing split sample. We train on half the data set, evaluate another half the data set, and then flip it around. When k is small, what might we be concerned about with the mean of the cross-validation estimate? The mean, well, the mean's not random, right? So the mean can't have high variance. But the mean compared to the, what's wrong with the mean compared to the actual expected test error? Where we actually, remember, we fit on f hat on all the full data set. So again, let's think about k equals 2. What happens when k is 2?
Small training.
The training set's too small. I'm fitting on n over 2 samples instead of n. This guy is what happens if I fit on n samples. So if n is not huge, then this could actually be quite different. And often cases, if the estimator is good, this might be too large, right? At a fixed value, for some fixed function f. If I'm not doing like model selection, I'm just looking at one particular fitting procedure, this might be too large. So it's biased. And we might think it's actually biased upwards. So it's biased when k is small. How about if when leave one out cross-validation with k equals n? We don't have that problem, right? Because we're training on n minus 1 data points at each round of cross-validation instead of n. So it's not going to really have the same bias. We're not too worried about it. What about the variance of the CV estimate? What's wrong with the variance of the leave one out cross-validation estimate? Well, what is the leave one out cross-validation estimate? It's the average of n things. So that's good. We're averaging over more quantities. But what do we know about those quantities? They're fit on different data sets, but those data sets overlap a huge amount. So CVJ fits f hat minus j, and CV like I fits f hat minus I. And f hat minus j and f hat minus I, they're fit on n minus 2 common data points, right? So they actually, the training sets overlap a lot, which means that these are going to be very, very correlated. So I'm taking the average of some very correlated quantities. What happens when I take the variance of the sum of things that are very correlated? That has a high variance, right? Because the variance of a sum is the sum of the variances plus the covariances of all the other terms. So in this case, that's going to be very, very high. So variance of CV, it's going to be very big when k is big. When k is small, like 5, the training sets don't overlap as much. They overlap in some sense, but not really nearly as drastically as they do when k is n. So look, it's the bias variance trade-off once again. just in a different form, in terms of choosing the number of folds for cross-validation. This is an estimate of the test error. We have problems if we take k to be like way too small or way too big. Heuristically, and in my own kind of completely, I suppose, not empirically validated personal opinion, I would always go with k equals 5 or 10. It's just the choice that I usually make. I don't think leaving out cross-validation is usually a good idea, because I usually find through, like I said, anecdotal evidence, nothing formal or like not a rigorous empirical experiment, that the variance is more of an issue when it comes to estimating the test error. So I'm more concerned about leaving out cross-validation than I am about 5 or 10-fold cross-validation. But I don't think that there's a uniformly accepted opinion. So do you agree with that?
There was this paper by, I forget the guy's name, it was really complicated. They tried to settle this issue, but it was so complicated that I think the answer is still we don't know.
Yeah. I think if there was a paper that somehow definitively settled this in a non-trivial case, it would be a very big deal, because everyone does cross-validation. But I'm not sure that's realistic. But anyways, like I said, there's to each side of the coin, small k or big K, there are things to be concerned about. But I'm usually less concerned about that. So, all right, we could, of course, do this at a bunch of different tuning parameter values, like if f hat was indexed by theta, we could just do cross-validation for every value of the tuning parameter, theta, so k and k nearest neighbors, record CV of theta, right, for every value of the tuning parameter, and then just choose theta hat to minimize the cross-validation error. Very, very common way to do model selection. Here's one thing that is, I think, kind of interesting that maybe some of you haven't learned in another class. We don't typically teach it because it's really informal, and there's nothing very rigorous to be said about it, at least not so far as I'm concerned. But it's an idea that came a while ago from this book on classification and regression trees. I think that's where it appeared first, this CART book. And that's called the one standard error rule. And first, we have to know how to estimate the standard error for a particular estimate of the particular cross-validation estimate. So here's what it is. We're going to define the standard error of some estimate CV. So I'm not putting in the tuning parameter notation here, because I'm just going to do it for a fixed fitting procedure for simplicity. I'm going to define it as 1 over root k times the sample standard deviation, which I don't know how else to write except for SD hat, just to note that it's like the sample standard deviation of CV1 through CVK. So take the sample standard deviations of these k numbers, divide by root k. That's how we define our estimate of the standard deviation of the cross-validation error curve, which we call it standard error. Where does that come from? You can look at the notes. It's not a complicated argument. It's just that if you try to take the variance here on both sides, right, you would get that it's 1 over k squared times the sum of the variances of these guys plus the covariances of all the other terms. And we're going to make the approximation that those covariances are small, so we're going to throw them away. That's only really valid when k is small, like we said. Otherwise, when k is big, that's not valid. So we only really do this standard error stuff when k is like 5 or 10. So I have 1 over k squared times the variances, times the sum of the variances of these. But since I assumed that the data are IID, each of these quantities are also IID. So they really all have the same variance. So it's like 1 over k times the variance of one of these. That's what our estimate of the variance of the CV, the final CV quantity is. And how do I estimate the variance of this? Well, I have k IID copies of it. I'll just take the sample variance. Or in terms of on the standard deviation scale, taking a square root, I'll just take the sample standard deviation. So that's what that estimate came from. And it's very useful because we can define a rule called the one standard error rule, which I'll draw for you pictorially as follows. Suppose this was theta, and this was our CV estimate, CV of theta. and we tried it at a bunch of different values of theta, and I'll just draw it as a curve. In practice, it would be discrete. Right? It wouldn't usually be continuous because we wouldn't really be able to do cross-validation on a continuous scale for the tuning parameter. And this is our usual estimate, right? We'll call it theta hat. It's the guy that minimizes the cross-validation error curve. But I have more information from the cross-validation process than just the mean, or the empirical mean. I also have the standard error quantity, which I can put on top of the cross-validation error curve and below. And it gives me an idea of the variability of my estimate of the test error. Right? I'm plotting here plus and minus one standard error away from the cross-validation error curve. The one standard error rule says, well, let's use these standard errors. In particular, let's suppose we're in a situation where as theta increased, I'm getting simpler models. I'm getting less and less complex models. If that was the opposite, if I decreased theta to get simpler models, then I just would reverse this rule. So let's suppose that this meant simpler models. So in the case of k and n, if theta is k, then that's true, right? The bigger k is, the less complex it is, at least in terms of degrees of freedom, right? We know that. So now what I do is I go to the minimizer and I draw a horizontal line that's one standard error above the minimum. So this is the cross-validation at theta hat plus one standard error above the minimum. And I move to the right in the direction of simpler models until the cross-validation error curve is one standard error from the minimum. And instead of taking this as my estimate of the tuning parameter, I take this guy, which I call theta tilde. And that's written formally in the notes. I don't think it's worth writing on the board. I don't think you'd get anything else out of it other than this picture. But check the notes if you want to see the precise definition. And the explanation is as follows. Up until one standard error, I don't know the difference between the cross-validation error, or really the test error, of theta tilde versus theta hat. Right? Because that's by definition, I've constructed theta tilde to lie within one standard error of theta hat, right, in terms of the cross-validation measure. So I may as well go with a simpler model. Right? If I don't know which one actually does better, I may as well favor the simpler model. Okay, it's pretty heuristic. Why one standard error and not two standard errors? And why not 1.5 standard errors? I don't have a good answer for any of those questions. I don't think it's really even known what this is doing at a population level. At the population level, cross-validation is estimating the test error. What is this estimating? It's kind of, it's not really clear what this is minimizing at a population level. All that aside, it works really well in practice. It can work really, really well in practice. So people use it, especially in a situation where the cross-validation error curve is really flat. If the cross-validation error curve looked like this, right, then the minimizer, especially the cross-validation error curve, was noisy because it's never going to be some smooth thing. The minimizer could have been here. The standard errors could have been quite big. And you could have taken a tuning parameter value that was up here somewhere. So that could have been theta hat. And this could be theta tilde. And it could really help out in a situation where the minimizer is not terribly well defined. So people use that in practice. If anybody wants to do a course project on the one standard error rule, I would personally support it because I think it's interesting and there's not very much known about it. But yeah.
Does this help still when your model is pretty heavily regularized? Because doesn't this sort of act as a type of regularization?
Yeah, so in that case, you'd be choosing the regularization parameter, right? So if we talk about regularization, which we will kind of, pretty soon, I guess, and throughout the course, then this might choose a regularization parameter that's not strong enough because we're looking to minimize the cross-validation error. If the cross-validation error curve is quite flat, you might get kind of weak regularization. This is saying I want the most regularization possible, subject to my estimate of the cross-validation error not being worse than the best one by more than one standard error. So it favors the more regularized model. Yeah?
If you have multiple parameters, which direction do you choose to go in? Because
Yeah.
the degrees might be along several directions.
Good question. I don't think there's a uniformly accepted answer. So just to rephrase it, if I had two tuning parameters, then it's a cross-validation surface. Right? I could look at all points whose cross-validation error was smaller than one standard error from the optimum point. But that might be that might be a 2D set. So which element do I pick out of that 2D set? Because I have multiple directions to look in. I don't think there's a uniformly accepted answer, but I think a good way to do it is to look at degrees of freedom. So we know that that is a way of measuring simplicity. So for every pairing of tuning parameters, right, theta and whatever the other one's called, phi, if I can compute degrees of freedom, then I get basically an estimate for the complexity of every model in that sublevel set, all the stuff that's one standard error from the optimum point, and I can just choose the pair of tuning parameters that gives me the smallest degrees of freedom. That's equivalent to this in most cases because degrees of freedom is usually monotone. So that's usually what we're doing here. We're taking the simplest model, it's like smallest degrees of freedom. Good question. All right, we only have a few minutes left, 5 minutes or so. So this stuff I'm going to cover again when I talk about nonparametric regression, but I wanted to get a head start because we have so much to talk about with nonparametric regression that I usually end up cramming this in to those lectures without much time. So I thought it really fits into this nicely. We can start talking about it. I think actually it's also on the homework, so you probably want to pay attention to this last 5 minutes. But the homework's not it's not too hard. You don't have to worry about this part at least. So we're going to talk about a particular type of estimator f hat, which is called a linear smoother. And that's an estimator that looks like this. So it's some function of the x points, which we'll call, some function of the x points, evaluated at x times yi. So this guy, this can depend on x1 through xn, the training points, right? x1 through xn. It can depend on theta if there's a tuning parameter. It can depend on a bunch of other external quantities, whatever. They can't depend on y, though. That's the important point. These weights cannot depend on y. So with respect to y only, if we think about this as a function of y, it's linear. That's why we call it a linear smoother. So we write it as w of x, some weight vector transpose y, the y vector. So it turns out that a lot of stuff that we talk about in parametric and non-parametric regression, parametric and non-parametric modeling in general, falls into this class. So for example, KNN is a linear smoother. It's a linear function of y's. All I'm considering is y's as the variables, and the x is fixed, right? Because I'm just taking an average of ky's each time. Which ky's I choose depends on x, but that doesn't matter. That's what goes into this part. Linear regression is a linear smoother. Ridge regression is a linear smoother. Turns out kernel smoothing, Mercer kernels, smoothing splines, sieves, kernel density estimates, all these things, they're really linear in some sense. Well, I guess the density estimate was not really a good example. But everything that we talked about for the supervised problem just there, those are all linear smoothers. So pretty big class, and we'll talk about all that stuff in detail later. But I wanted just to say that we can do things pretty precisely for linear smoothers, meaning that we can actually compute degrees of freedom for linear smoothers very precisely, and we can do the bias variance trade-off very precisely for linear smoothers. So I'll do degrees of freedom right now, and on your homework, you're going to do the bias variance trade-off. And you can see that for linear smoothers, we kind of understand a lot. So it's a good class to lie in. Let's write the fitted values. So again, we'll use this notation f hat to mean the vector f hat of x1 through f hat of xn. For a linear smoother, we know that we can actually write this as just a bunch of linear combinations of y, right? This is w of x1 transpose y, all the way through w of xn transpose y. And so if I just collect these w vectors to the rows of a matrix, I can just write that as S times y for some smoothing matrix S. So just again, just to be perfectly clear, that matrix S can depend on X, can depend on tuning parameters, it can depend on anything else that's external, but S is not a function of Y. It's just some fixed matrix once I fix all those other quantities. So another way to remember the linear smoother is that the fitted values are just a linear operator times Y, a matrix times Y. And now you can see, why is that true for linear regression? Well, what were the fitted values in linear regression? There's the hat matrix times Y, right? X times X transpose X inverse, X transpose times Y. So that S was that particular matrix. And you'll see that we'll have, like I said, many more examples of that coming up. What's the degrees of freedom? Let's do that before we convene today. Degrees of freedom of a linear smoother. Well, degrees of freedom of f hat is 1 over sigma squared times the sum of the covariances of f hat of xi and yi. And just to remind you, when we talk about degrees of freedom, like we said before, we think of the x's as fixed and the y's as iid f of xi plus errors, where the errors have mean 0 and variance sigma squared. That was our setup. Okay, so we could go ahead and compute that just by plugging in w of xi transpose yi. But there's another representation for degrees of freedom that's more useful for this. So I want to use that instead, and that's this one. It's the trace of the covariance matrix of f hat and y. So the covariance between two vectors, right, I can write as a matrix where each entry gives me the covariance between one component of one and one component of the other. So this is a matrix whose ith, jth entry is the covariance of fi and yj. So the covariance of fi and yi lies in the diagonal of this matrix, and when I sum those up, or I take the trace, that's what the trace is, right, the sum of the diagonal entries, I get this. So that's another way of representing it. It's just more convenient. And now let's plug in sy. What's the covariance of sy and y? Some of the stat students in here were probably TAing for like, what class would that be, 217 or something? You guys know this, is all I'm saying. What's the covariance of sy and y? So covariance is linear, right? I can always pull it doesn't depend on y. So as far as the covariance is concerned, this is fixed. So it's s times the covariance of y with itself. So it's s sigma squared, right? Because the covariance of y with itself is sigma squared I. So iid distributor n of variables with variance sigma squared. So it's 1 over sigma squared times the trace of sigma squared s. The sigma squared comes out and cancels with the sigma squared there. We just get trace of s. All right, pretty handy, because for any linear smoother now, we can, for example, do that degrees of freedom correction that we learned to learn its test, to get an estimate for its test error. Right? We know that the optimism, the difference between the training error and test error, is this. This is actually not an estimate for the degrees of freedom too. It's an exact calculation in the case of linear smoothers. It's exactly equal to the trace of s. So what is this for? What is this? Let's just check a few cases we know, and then we'll head out. For when f hat is y, s is the identity, and the trace of s is n. So we learned that already. The degrees of freedom of the estimator that takes in y and gives back y is n. When f hat is y bar in every component, s hat is the matrix that averages, it's 1 over n actually in every row, in every entry. And so its trace is 1. When S is the matrix that gives us the k and n fit, you can check that its trace is n over k. Got it right again. For linear regression, let's do that one real quick. So S is, I told you, was equal to x times x transpose x inverse x transpose. Right here, we're in the world where we assume x is fixed. So what's the trace of S? Well, there's a cyclic property of trace, which means that I can always take a matrix and rotate it around within the trace. So I get the trace of x transpose x inverse, which is, if x is n by p, then this is just equal to p. So we just learned that the degrees of freedom of linear regression, if I have p predictor variables, is p. Okay, and we can do more examples like that when we get to nonparametric regression. All right, that's it. We won't see you on Monday because it's MLK Day, but we'll see you on Wednesday.